Welcome to the first global webinar of CU Aerospace, or CUA. I am David Carroll, the president, and I'll be presenting an overview of the company and with a focus on the space technologies. First, to clear up some confusion that happens now and then, CUA stands for Champaign-Urbana Aerospace. We are located in Illinois, and we are not affiliated with Colorado University. We were founded in 1998. Our first decade was largely R&D focused, and then the last decade we've been transitioning towards more of a product company with a product focus. We purchased a building in 2018, a 10,000 square foot mixed use office lab space. We have 3,400 square feet of lab space, and we have a 200 square foot ISO 7 clean room. We have 30 employees on payroll at this point, and largely our success is due to their acumen and capabilities to handle and tackle these multidisciplinary problems that we address all the time. So the CUA specializations, we have a number of different areas, a fairly broad range of specializations encompassing aerospace materials, plasma and laser systems, space systems, and then modeling and simulation. The focus of today's talk, of course, is going to be towards the space side of our work. So let's start off with the hardware technologies. Sort of preaching to the choir here in terms of micropropulsion being useful for CubeSats. There are a broad range of different technologies with a large number of trade-off characteristics for thrust, volume, power, cost. We have put together 5 technologies that I'll talk about in more detail on the next couple of slides. But interestingly, these technologies are being productized more by small businesses and not your classic large companies. And these days you've got SpaceX, Blue Origin, and others talking about thousands of small satellites. So this provides what we view as a really exciting opportunity for some of our technologies. Further, there is the real need for deorbit capabilities on these small satellites to prevent the future accumulation of more space debris than we already have, because we need to avoid what's called the Kessler syndrome. So focusing in here on our micropropulsion systems, we start on the left with the PUC, or the propulsion unit for CubeSats. This has a really tiny microcavity plasma discharge in it, and you can see an image of the plume from the PUC system here. And this uses SO2 propellant, which is a unique propellant. The next offering is the CubeSat High Impulse Propulsion System, or CHIPS, and this utilizes self-pressurizing liquids, for example, R236FA, and a micro resistojet as the primary warm gas thruster. We've also incorporated 4 ACS thrusters in this particular prototype. The next one is what we call the monofilament vaporization propulsion system, or MVP. It utilizes 3D printer technology to both feed and melt a spool of a polymer Dillon propellant, and then we utilize the resistojet, very similar to the CHIPS one, to vaporize and provide thrust. And then the 4th offering is the fiber-fed pulse plasma thruster. This also uses a spool of polymer fiber. In this case, it's Teflon. And then we have a high voltage discharge arc that ablates a little bit of the Teflon with each pulse. You can see an image here of the plume. And then the fifth offering that we have is the monopropellant propulsion unit for CubeSats, or MPUC. And you see an image here of the thruster head. This is all of actually about 3 to 4 centimeters in length, so it's blown up here in this image, but you can see it glowing red hot in the catalyst bed region. So moving on to some of the performance characteristics, I'm not going to cover every number in this table, but I'll cover some of the more common ones of interest: the specific impulse, the thrust, and the total impulse of these systems. So the first three, the PUC, the CHIPS, and the MVP systems, these are all electrothermal systems. And so you end up with a specific impulse on the order of 60 to 70 seconds. They have different thrusts, but order 5 to 20 millinewtons. And then the total impulse is largely dictated by the volume of the system. In this CHIPS system, that's a 865 cc volume system. So you see it's got 471 Newton seconds of total impulse. But the PUC system has 184, but it's only packaged in a 0.35 or 350 cc system. The MVP system, sorry, let me back up. That's the PUC and the CHIP systems are self-pressurizing liquids for the propellant. So you have a pressure vessel and you have valving, both of which can add significant cost to the overall system. So the advantage of the MVP system is that the fiber spool of Dillon eliminates the need for any sort of pressure vessel, and there's no valving associated with it. So the MVP system is actually our lowest cost entry, and we hope that it will be attractive to, for example, universities that are on more of a budget. Okay, now let me go to the FPPT system, the fiber pulse plasma thruster. You can see here an illustration, there's the white, that's a fiber spool in the back. Got capacitor banks and electronics internal, and then the discharge. We are building right now 2 of the 1.7U systems, and this gets pretty exciting because by having the ability to control the flow rate of the propellant itself and having some control on the capacitor bank energy, we are able to tune the ISP up to very high levels, as high as 2,400 seconds we've measured, at thrust levels on the order of about 0.3 millinewtons. But most excitingly, at the 1.7U or 1.7 liter size, we estimate that we can achieve over 20,000 Newton seconds in total impulse with the FPPT system. And then the last entrant, the monopropellant system, in a 1.5U size, this is our highest thrust system, giving 160 millinewtons. And oops, this unit should be seconds, not milligrams per second. And then the unit above it should be milligrams per second. Anyway, this system should provide 1,500 Newton seconds in its final form. And the FPPT system, we should have TRL6 by end of this year. And then the MPUC system, we're anticipating TRL6 by August of 2022. Okay, so let me move on. The 2 fiber-fed systems are going into what is called the dual propulsion experiment, or duplex CubeSat. And this is an exciting situation for us because NASA STMD awarded us with one of their tipping point awards. And so we are fully funded for the fabrication, qualification, launch, and in-space operations of this 6U configuration. You can see an illustration of the FPPT plume here, and then we're going to have the MVP system on the other side. So we'll be able to get flight heritage for 2 of our systems. This program has already started. Some fabrication has started, but we will be really entering the fabrication and integration stage next year, with launch anticipated in mid-2022. So the next technology, hardware technology, is the Distributed Inertial Sensor Integration, or DISI kit. And this is intended for enhanced spacecraft sensing and navigation. What we are doing here is putting distributed inertial measurement units around a spacecraft. This illustration is on a larger modular spacecraft where you can put the daughter cards on solar panels and solar arrays, as well as other modules in the configuration. We are actually planning at this point to include the DISI kit onto the duplex satellite. And so we're going to have a couple mounted on the solar panels on the outside, and then we will have some on the inside of the system. And the objectives for that will be inertial navigation validation, jitter identification, system alignment, visual inertial navigation, and then just general on-orbit long-term performance. By the way, I should mention that if you have any questions as we're going along, feel free to put those into the chat, or I'll leave about 5 minutes at the end to answer those questions, and then actually I'll stay on the Zoom call afterwards so that we can, if anybody has more detailed questions, we can address those. Okay, the next hardware is called GRASP, for Guideless Resilient Androgenous Serial Port. This is meant as a modular assembly interface with flexibility, and the modular spacecraft, for example, as illustrated here, you've got these different modules or pods that can be docked together using the GRASP mechanism. And this is an illustration of the second prototype, where you see the alignment cone and docking mechanism in the center, having then power pins and also data pins, so that you can transfer both power and data between the modules. So then this can be used potentially for fixed modular capture, where you've got a satellite holding 2 modules, or even free flyer capture, where you are just grabbing hold of a freely flying module in space. And oops, I meant to add that we have demonstrated in the lab robotically both fixed sled and air-bearing sled captures with GRASP. So we are very intrigued by this technology, and we'll be coming out with the actually the GRASP 4 prototype here by the end of the year. Okay, moving on to CubeSat. So we also have been pursuing solar sail technologies for the last 18 years or so. CubeSat is a 2-module CubeSat. Each module is 1.5U. So you've got A and B, and each module carries 125 meters of solar sail material. So they are taped in the middle and have a total length of 250 meters. CubeSat was launched in December of 2018, and it was launched on ELENA 19 on a Rocket Lab Electron launcher. It is in orbit, and mission ops are presently scheduled for mid next year at this point. and we of course hope that things go well. Now let me switch to the space systems software side of the company. We have a lot of people involved with astrodynamics in the company, and astrodynamic problems are very nonlinear. So we have two software tools, one called NL-PAROPT for nonlinear parallel optimization tool, and CompNot for CUA OpenMP nonlinear optimization tool. These are sequential quadratic programming solvers that intelligently choose algorithms to solve these QP problems. And they exploit parallelism for multiple computer architectures. One is the distributed memory, and one is shared memory. And we've demonstrated scaling of these to different cluster sizes, and the intent is to be including these, well actually we've already been doing astrodynamic simulations for sea salt, and then we intend to also be doing GMAT in the future. So these will become available probably early next year. Dillon stands for Dynamically Leveraged Automated N Multibody, or Dillon, Trajectory Optimization Software. This is intended for difficult, complex trajectories that are very common for low thrust situations. The illustration here is you have a satellite spiraling out from Earth orbit, from low Earth orbit, going through various inclination changes, and then ultimately going to the moon and settling down in the circular orbit there. Now this looks a little strange, this illustration, and that's simply because what we have done here is projected a 3D low thrust trajectory onto a 2D plane. But anyway, the Dillon system or software allows enhanced mission design capabilities. It should also allow higher fidelity accuracy solutions in less computational time. And perhaps most importantly is that it provides an automated process for finding feasible solutions for the mission designer, and that translates to reduced number of labor hours. The next software tool that we have for space systems, this is called Scepter, and it is for designing optimized reconfigurable spacecraft architectures. So again, we point to these modules. These are designed as meter by half meter by half meter, and you see the little white markings here. That's meant to be a grasp system at these different points so that you can reorient the modules to optimize the configuration. And this can also potentially show how one might be able to get away with fewer modules than you might design by hand. It involves a genetic algorithm solver for the optimization problem. But here's on the left, you've got the input GUI where you enter the modules that you're interested in and also mission objectives. We anticipate that this will be available in December of 2020 in both MATLAB and Python compatible software packages. Now shifting to some other CUA technologies that have relation to space, the Vasc Tech material for vaporization of sacrificial components technology. We sell this as fibers, filaments for 3D printing, or even extruded sheets. In all forms, it is a sacrificial material that once it is incorporated into the larger structure, for example, a composite, that you can heat that composite and pull a vacuum on it and the sacrificial material will vaporize. So you can be left with a composite here, for example, with these microchannels that are woven into the composite. And this was used as a micro heat exchanger, and you can see the frost on the outside of this micro heat exchanger, this test article. It can also be incorporated into recuperators or regenerators or even active flow space radiators for space applications. And so this has been an ongoing technology that is slowly growing. And then the last technology that I was going to talk about on the space side is plasma sterilization technology that we have used in the past for killing E. coli. And on the left here, you see a photograph of the system in operation. You've got the actual discharge that creates excited singlet oxygen, and the sterilization chamber, which then in the middle, you can see a view from the top. And here we were testing its ability to kill E. coli. You see the control sample. Then after 5 minutes, you see a 4 log or 4 order reduction in the E. coli. And then after 10 minutes, you see a 6 log or 6 order of magnitude drop in the E. coli. So this is proven to be very effective against these various pathogens, and actually should be very effective against COVID-19, which we're hoping to test out at someday in the future. But key advantages are rapid, low operating cost. It operates at near room temperature, and then total load unload cycle times of approximately 30 minutes. We have a closed loop design, and then we are just now beginning a NASA SBIR program to evolve the Spark technology for the sterilization of spacecraft components, sampling tools prior to collection, biocontainers, and then hopefully down the road to manned missions as well. So at this point, the products that the company has, we've got 3 of the micropropulsion systems, MVP, CHIPS, and PUC. We've got Vasc Tech. Thermosys is a MATLAB toolbox for the air conditioning or refrigeration industry. We also have a 3D full multi-physics code called Blaze. And then for the aircraft industry, we have cyclotronic arc plasma actuators. Over the next 15 months, we anticipate having the fiber-fed pulse plasma thruster available. That actually should be available close to the end of this year, or maybe early next year. The GRASP system in the same time frame. Scepter also in the next few months. NL Paropt CompNot in the next few months. So this year is clearly a big year for us. And then the Dillon software should be available in approximately a year and a half from now. So I will close out this overview summary of we are a 22-year-old business now. We've got 5 micropropulsion offerings for different customer needs. And then other niche space systems include the GRASP interface mechanism for docking assembly, and space system software packages including Dillon, Scepter, and parallel optimization problem solvers. And lastly, we see ourselves as an emerging company in this ever-growing space ecosystem.